Okay, what'd you come up with? Integers? Yeah? Yeah? Okay. So, which equation did you solve and why? Okay, the bottom one for y because its coefficient's already +1 and you're smart lazy. Alright, that's a good mathematician. So we're just going to, here, I'll do it in red. We're just going to subtract this 5x from both sides. And then we should be able to substitute that right here where y is. And we're going to use parentheses. Remember, parentheses are our friends. 3x subtract 2, big set of parentheses, equals 15. And then we're going to put that 12 subtract 5x right there. And then at this point, how do we know we're on the right track?
You do it.
You do it? Yeah? But before, what? Okay, we only have one variable in our equation now, don't we? Okay? So that means that's good, right? So we can solve this. We can do it. Subtract 24 plus 10x equals 15. We can add our like terms. And I'm going to go ahead and add 24 to both sides. So that's 39, I hope, because I want it to be divisible by 13. Because I know the answer to all of these are integers. So there we go. X is 3. And if x is 3, then y is 12 subtract 5 times 3. So 12 subtract 15, and y is negative 3. So here's our solution. And if we were to graph those two lines, that's the point where they would intersect, right? That's the one point they have in common. Okay. So that's a good review. All right, now we have talked about 4 different segments in a triangle. We talked about perpendicular bisectors, angle bisectors, what else? Altitudes and medians, right? We talked about how they are all concurrent. We talked about what the deal is with that point of concurrency, whether it was equidistant from the vertices or equidistant from the sides, or remember that 1/3, 2/3 relationship for the median, or what about the altitudes? What about the orthocenter? What was the deal with the orthocenter?
Useless.
Useless. We don't do anything with it, do we? It's just, but it is cool that all the altitudes are concurrent, right? And you've got notes on all of those things. Okay. So now we're going to talk about a different type of segment called the mid-segment. Okay. What's that?
How do you find the what?
How do you draw the altitude? Well, I'll show you that later. Again. Okay. Mid-segments of a triangle are different than these other 4 we've been talking about, because mid-segments are not concurrent. So this is a different kind of thing, all right? What a mid-segment does is, rather than like a median, it goes from the vertex to the midpoint of the opposite side, okay? A mid-segment goes from midpoint to midpoint. So there's still 3 of them, midpoint to midpoint, midpoint to midpoint, okay? But they don't all intersect at that single point. They're not concurrent. Now, construction of them, okay? We still need to find the midpoint of each one, just like we're going to draw a perpendicular bisector or a median, okay? So this, again, it's the same deal. If I go more than halfway on the longest side, and I'm going to make some big arcs. Okay, remember, from here to there, perpendicular bisector, we could draw it, couldn't we? Or we can mark where the median is, and we can draw, or sorry, midpoint is, and we can draw a median. Okay, but today all we're worried about right now is where is that midpoint. Okay, so I'm also going to come up here to this other vertex, and I'm going to come around like that, and so that I can find all three midpoints. And it's easiest to find all three at once by setting your compass one time and then doing all three arcs so that you end up with all three of these intersections that you can find the midpoints with. Okay? So today we're talking about a mid-segment. A mid-segment goes from the midpoint of one side of the triangle to the midpoint of the other side of the triangle. Okay? And I just want you to look at it. We're going to call this one DE. I want you to look at DE for a minute. Okay? And I want you to think about, what do you think about it? I want you to think about, what do you think about it? That was horribly said. Yes, Blake?
I think you're making another triangle and there's like flip. Like, you think there
What? This triangle here?
Yeah.
What do you think about that triangle up there? That it's flipped?
Yeah, it's like there's a point down there and you're gonna draw. And you're gonna unite the point and it's gonna look like that one on top above it.
So this one down here, when I draw it, is going to look like the one above it?
Yeah.
What about the one right there when I...
I think they're all the
What, you think all four of these? Okay, I'm going to get there. We're going to get there. It's going to be similar. So those four are going to be similar to the big one. Man, you guys just jumped to the end of the lesson. What about just the segment DE?
Is it parallel to AC?
It is. It is parallel to AC. It is, in fact, parallel to AC. And it's something else compared to AC. Do you think it's perpendicular? I don't think it's perpendicular to it. What do you guys think? What?
It's half of it.
Yeah, it is. It actually is. It actually is half the length of AC. So it's parallel to AC, and it's half the length. So this is the mid-segment theorem, that the mid-segment of a triangle is parallel to and half the length of the side that it doesn't intersect. How do I say that? The third side. It is half as long as the third side and parallel to the third side of the triangle. So if I draw in the other mid-segment, EF, see how it's parallel to AB and half as long. And when I draw FD, it's parallel to BC and half as long. Okay? So if all of its sides are exactly half as long as the original, can you see why it would be similar? Now, we haven't really talked about similar too much yet, but you know, if I have one triangle and all its sides are exactly half the length of another, okay? And can you guys see all four of the little triangles in here? They're all congruent triangles. Okay, all four of these are congruent triangles. We've talked about what that means a lot. And then all four of them are similar to the original. But the mid-segment theorem is that the segment containing these 2 points from mid-segment to mid-segment will be parallel to and half as long as the third side of the triangle. Okay? So, not concurrent. No point of concurrency that you have to remember. That's good, right? You already know how to find the midpoints, don't you? Okay, we've been using construction and finding those all the time. Okay, let's think about how to prove this. You're just dying to know how to prove it, aren't you? So what I'm going to do is I'm going to use a coordinate proof. And I'm just going to draw a triangle in here. We're going to call it point O. I'm just placing it here, 0, 0. Point C, I'm going to call this point, I'm going to call it 2 times P. And then what would its y coordinate be? 0. Okay. And then this one up here, point B, I'm going to call it 2 times Q and 2 times R. Now, since it's my triangle, I can place it in the coordinate plane however I want. And I'm going to place it conveniently, so one of its vertices is at the origin, and one of them is on the x-axis. And then I'm also going to name these. I mean, if I want to call that 2 times P, that's what it is, right? Now, that doesn't mean that actual x-coordinate is an even number even, though. Okay? It's just that it's because, you know, this midpoint right here, can you guys think of what its coordinates would be? 1p, 0. Yeah. And then what about this midpoint right here? Okay, so think about it. Think about the midpoint. We're going halfway on the x-coordinate from 0 to 2q. What is halfway from 0 to 2q? 1q. And on the y, on the vertical, from 0 to 2r is 1r. Yeah? Okay. And then let's think about this point over here, point E. So I can have my mid segment right there. Okay, now this one's a little bit more of a thing, see, because we're going to have to use the distance formula on the x coordinates, because I think we're going to have to go 2q plus 2p divided by 2 to get the midpoint, aren't we? Okay, well, let's think about that for a minute. 2q plus 2 times p divided by 2. Well, that's the same as 2 times the quantity q plus p divided by 2. And then what's going to happen to our 2's right here? There you go. Okay, so that's the x-coordinate, q plus p. And then the y-coordinate's a little easier. 2r plus 0 divided by 2. Yeah, it's r. Okay. Now, here's the thing. Let's think about the slope of this line right here. You guys already know what its slope is? Raiden, what is its slope?
0.
Yeah, it's 0. Okay, its slope is 0. Well, let's think about the slope of this line.
0.
Okay, now are you sure it's 0?
No.
Let's check this out. On the top of the fraction, we're going to have r subtract r. What does that give us? 0. So if the top of our slope, right, if the numerator is 0, well, as long as the denominator isn't 0, we better make sure the denominator. What's q subtract q plus p? Just be p. So it would be 0 over p. Well, what's 0 divided by p? Okay, so now we're sure. The slope of that line is also 0, isn't it? Okay? Now, let's think about the length of the segment. What is the distance from O to C? The measure of OC? 2p. Very good. So how long should this one be? 1p. Well, how do we find out if that's really true? Well, for one thing, does the y-coordinate change? No, so we have no change in the y-coordinate. What is the change in the x-coordinate? From q to q plus p. What's the change? It's p. Right? It's p. So you can kind of see it. But we could even use the distance formula for DE. The measure of DE would equal the square root of, okay, x, that's q, subtract this x, which would be q plus p, squared plus r subtract r squared. Now does that seem weird that I did this in parentheses? But I have to subtract the q and subtract the p. So if I'm going to subtract a quantity, that quantity has to be in parentheses. So q subtract q, well, that's 0, isn't it? And then subtract p. So it's actually the opposite of p squared. And then what's r subtract r? 0 squared. Well, what's the opposite of p squared? P squared. Very good. Okay, there you go. P squared. So negative p times negative p is positive p squared, right? And then 0 squared, of course, is 0. And what's the square root of p squared? Yeah, it's p. So the distance from D to E is 1p. The distance from O to C is 2p. I think I just proved something. Yeah? And I proved they're parallel, didn't I? Didn't we? What's that? Yeah, same slope. Now, could we do that for that midsegment right there and this one? Yeah, they're parallel. We can prove their lengths. This one's half as long. We could prove it for this one here as well. It's going to be parallel to that line and half as long as that third side of the triangle. This is the midsegment theorem. It's a theorem because we can prove it, right? It's not just a postulate or something. It's not like we just looked at it, we just eyeballed it and said, well, it looks parallel and it seems to be half as long, right? That's a bad way to go about your life. A good way to end up dead. Okay. Idolatry. Yeah. Idolatry works when you're building a doghouse. Not so much when you're building a people house. Right? Okay. Okay, so what kind of questions are we going to get? Look at the bottom of page 331. You'll see a truss there. So that's a roof structure. Notice all the triangular bracing there, all those triangles, right? So notice that most of the bracing, it's a mid-segment, right, of a larger triangle. So everybody look at RT for a minute. Can you see it? How long is it? 90. Okay, what about UV then?
45.
It's 45, yeah. It's half the length of that third side. CVW? Well, what about RU? It's also 57, yeah. What about US? It's also 57. What do you guys know about point U? It's the midpoint, isn't it? Okay. What about SR then? Okay. At least it's 114. It's 2 times 57, isn't it? Okay. I don't think we're going to have anything horribly difficult here. I will say this. Let me just make a quick drawing. And I'm going to draw in one mid-segment, midpoint to midpoint. Yes, I'm doing this by idolatry right there, right? But those two are parallel. Do you see the transversal, everybody? See those two angles right there? What do we know about them? Yeah, they're congruent. Why? Because what's their relationship? Did I hear it? Corresponding, right. And then what about here and here? They're corresponding, aren't they? Okay? Corresponding angles. So these two are congruent, these two are congruent. And then I think when you start looking at, okay, these two being parallel, that's not very parallel-y, is it? Okay? But do you see how we're getting corresponding angles? So when we draw all three of these in, you know, these two angles right here and that one. And this one. Those two, this one, and this one. No, this one. This one here, this one here, this one here, that one there. So these four small triangles, all of their angles are congruent. Angle, angle, angle. Right? Does that prove the triangles are congruent though? Angle, angle, angle. It just shows they're similar, doesn't it? Okay. Okay, here's your assignment. Nope, that's it.